this is the box problem. What we have here is, we're going to make a box. We have a sheet of paper, which is 16 inches by 30 inches, and what we're going to do is, we're going to cut squares of equal size out of all four corners. All right, we're going to cut those out, and then throw them away. With the shape that remains, as you see, we have like a box, open top box, that has these four flaps. Fold up the flaps, the box is going to have a certain volume. So the question is, how far do we have to make our squares? How far in do we cut in order to get the maximal resulting volume out of our box? So what we're going to do, we have to model this somehow. So you think, what are we going to make our variable? Well, anything that you don't know what it is, that's what you make your variable. So what we don't know is how far in we have to cut. So I'm going to call these sides x. The length of which we cut, the sides of the squares are going to be x. Once you have that done, you figure based on x, what's the volume going to be? Well, you're going to fold it up, it's going to make a box. The volume of the box is length times width times height. So what are the length, width, and height of the resulting box? The length part will be 30 minus x minus x. It's going to be 30 minus 2x. I'll fill that in here. 30 minus 2x. The width of the box will be something similar. It's going to be 16 minus 2x. So multiply that by 16 minus 2x. And the height of the box is just going to be the size of the flaps that you had cut out. So it's just going to be times x. So that's the volume equation. We want to maximize this. On what interval should we be maximizing this? So what are the acceptable values of x that we are talking about? You look back at the context here. What's the largest and smallest amounts we can cut out of this? Well, you can cut out 0. Right? If you don't cut it at all, you really don't have a box, or you have a box of volume 0. So v of 0 is 0. But what's the largest that we can cut in? Well, look at what x is. X can only be half of the distance of the length of the shortest side. Right? If that's x and that's x, the largest x can possibly be is 8, because the whole thing is 16. So maximize the function on 0, 8. But of course, if you cut 8 in, you're again going to get a volume of 0 because your box won't have any width. So v of 0 is 0. And you can tell that just by plugging those numbers in here as well, right? If you plug in 0, you get the whole thing drops out. And if you plug in 8, you'll also get 0 because you get 16 minus 16. That'll go away. So obviously the maximal value does not occur at the endpoints. So we need to hunt for critical numbers. Multiply that out. This is what you're going to get. All right, so this is our volume function. We want to maximize it on 0, 8. So we hunt for critical numbers. Got to take the derivative. So you get v prime equals of x squared minus 184x plus 480. And we want to find where this thing is 0. We have to know it factors. And it factors into 4 times x minus 12 times 3x minus 10. So it appears we have two critical numbers here. So in addition to v of 0 and v of 8, we have to do v of, the critical number is 10/3. And we don't have to include 12 because 12 is not in the interval. We can't cut out 12. So it's just a meaningless number in the context of what it is that is going on. So v of 0 is 0, v of 8 is 0, v of 10/3. If you take the 10/3, plug it back into the original function, work it out, what you wind up with is approximately 726. And that's the only critical number, and so since the maximal value must occur at either the endpoints or a critical number, that's as good as it's going to get.